Yes, you are.
Okay, that's good. Okay, let's continue with our numericals today. And I will conduct a test on Sunday. We have our next class on Sunday, I guess. So I will take a test on
About
Sunday.
the electromagnetic induction, EMF, and all the formulas.
Yes. It will only include the numericals. Only numericals.
Oh, okay, only the miracles. All right. At what time are you gonna take it?
In our class, during the class, because we have got enough time to practice the numericals, and yeah, I will take the class. I will take the test during the class. Because we have practiced the numericals, we have not got any, like any weekly planner that you're gonna follow in your school in the coming week. So I guess we have to continue practicing these numericals in the next week as well. So we have got enough time during the classes to practice the numericals. So I will conduct the test during the class as well.
All right. So, meaning we will just like take the class lesson for the test. Won't take like any extra like or teach anything new, right?
Yeah, yes, I will only conduct the test of the numericals. It will only include the numericals.
All right. Okay.
Okay. Okay, so let's start with the numericals. Let me just write some of the numericals so that we can practice it. Okay, let's see a few Lenz law problems. For example, if we are given a question, okay, for example, we are given a question that a rectangular loop, it is pulled to the right out of a magnetic field and the magnetic field is going into the page. You have to tell the direction of the induced current. How can we find the induced current, the direction of the induced current? What do we do in the first step?
Okay.
In the
So,
very
okay,
first step,
rectangle.
we have to check whether the flux is increasing or decreasing. What will be the effect on the flux? This is what we check in the first step. Is the flux into the page increasing or decreasing? It's written that it is pulled to the right out of a magnetic field. Out of a magnetic field means is the flux getting increased or decreased? The rectangular loop is pulled to the right out of a magnetic field. It is being pulled out of the field. So what would be the effect on the flux?
For the flux, okay.
The
It is
rectangular
out of
loop,
the,
it
yeah.
is pulled out of a magnetic field. If I say that I have a loop and I place it into a magnetic field, after that I start pulling it out of this field. Out of this field means that I am taking it away from the field. So what would be the effect on the flux? Flux is simply the number of magnetic field lines that will be passing through that loop. So if I start taking a loop away from the magnetic field, what would be the effect on the number of lines that would be passing through it? Will they increase or decrease?
It will be increased, right?
Increase? How? If I have this rectangular loop and it is placed inside this magnetic field, after some time I start taking it away, it is being pulled towards the right out of a magnetic field. For example, the direction for the magnetic field, it's from left from right towards the left, and after some time I start taking this rectangular loop towards the right out of the magnetic field means pulling it away from the magnetic field. So previously it was placed at this point, but after that I started moving it away from it, and after some time I move it over here. It means that I have moved it away from the magnetic field which was going into the page. So it means that the flux will decrease because I am moving it away from the magnetic field. If you move something, if you move a loop or a coil towards the magnetic field, the flux will increase because more and more number of magnetic field lines they will start passing through it. But if you pull it away from it, the flux will decrease. In this case, we are pulling it out of a magnetic field. So in step 1, we have identified that the flux is decreasing.
Okay.
The flux is,
Decreasing. Okay.
yes. After this, we identify that what would be the direction of the induced magnetic field. This is the actual magnetic field in which the loop is present. But when the flux will decrease, what will happen? When the flux decreases, what happens after that? The system always opposes the change. It will oppose this change of decreasing the flux. So it will try to increase the flux. How will it increase the flux? It always, when the flux decreases, it always increases the flux by producing the induced magnetic field into the same direction as the original magnetic field. What was the direction of the original magnetic field?
Oh, the direction of the original magnetic field was out of the page, right? Into the page, sorry.
It's into the page. So the system will
Yeah.
try to oppose this decrease, and to oppose this decrease, it will create an induced magnetic field which will also be directed into the page. So in step 2, we have to identify the direction of the induced magnetic field based on the effect on this flux. Like we will get the step 2 from step 1. First, we have to identify whether the flux is increasing or decreasing, and then according to that, we will see that what will be the direction of our induced magnetic field. So, induced magnetic field, it would it will try to increase the flux, and increase the flux means that it will create a flux that will be in the same direction as the original magnetic field so that the flux can be increased. Same direction. So its direction would be into the page. After that, in step 3, using the direction for the induced magnetic field, we will check the direction for the induced current. Which rule do we use to find the direction of the current if we are given the direction of the magnetic field?
To find the direction of the current, we use the left hand rule, right? So,
Right, right. It's right hand rule.
but
So we will
okay.
use the right hand rule. And you have to simply point your thumb in the direction of the magnetic field, and the curl of your fingers will give you the direction of the electric current. Right hand rule. So if your induced magnetic field is into the page, you have to point your thumb towards the screen. If you are if you have the magnetic field going into the page, we point our thumb towards the screen, like away from it, away from us. And if it is out of the page, then you have to point your thumb towards yourself. In this case, it is into the page, so we will point our thumb towards the screen. And what would be the direction of the curl of our fingers?
towards the screen. So the direction. Okay, so it would be clockwise, right?
Very good, excellent. So the induced current, it would be clockwise. Okay, if now I ask you what would be the direction of flow of current in the top wire of the rectangular loop, what would you say? In the top wire of the rectangular loop, what would be its direction? A rectangular loop, it consists of the four wires, two horizontal wires and two vertical wires. If I say you have to tell me the direction of this induced current into this top wire, what would be its direction? You are given that the current it is flowing clockwise. Now you have to tell whether it will go from left to right or right to left.
Okay, so we're moving. Our fingers should be pointing outwards or inwards in this.
Outwards or inwards? No, you just have to tell me that if we have the induced current which is moving in the clockwise direction, in the top wire, will the current move from left to right like this or from right to left like this? Which is correct? The current is clockwise. If it's clockwise, if I draw this direction for the current, that it is moving from right towards the left, it will come down from here, then go up to this point and then up to this. No, sorry, it has to move up like this. Is it clockwise direction or the anti-clockwise?
This is anti-clockwise.
It's anti-clockwise. It means that this is not the correct directions that I have given. So we have to draw the current that is going in this direction, then coming down, then going in this direction, just like this. Is this clockwise current?
Yeah, it is.
Yes, it is. Now, if I ask you what is the direction of the movement of current in the top wire, you can simply say that it is moving from left towards the right. You can see at this arrow, it is pointing towards the right. So in the top wire, it is moving from left to right, like this. Clear?
Yeah, it's clear.
Okay. Let's see one more example.
Okay.
Okay, so let's say we are given the question that a coil it rotates clockwise in a field into the page. At the instant when the right side is moving upwards, we have to find the current direction in that side. Which rule will we use?
First, okay, so there's a, okay, undo the page, then
Which three things are given? We have to find the
The
current. We are given,
yeah,
yes,
yeah, we are given the magnetic field, and
very good. We are given the
I think this
magnetic
is.
field.
And is this the
Mhm.
motion or
Yes, it's the motion moving
upwards?
upwards.
Okay,
So, yes. So, which rule will we use when we are given the current, magnetic field, and the motion? Which rule do we use?
the right hand rule.
Yes, it's the Fleming's right hand rule.
Yeah, because
So,
of
we'll do,
motion, not force, right? So
yes. So, it would be Fleming's right hand rule. So, according to Fleming's right hand rule, which of the finger will point in the direction of the field, which will point in the direction of the motion, and which finger points in the direction of the current?
yeah, it will move leftward the current's direction if we apply that rule. Yes,
No, like you have to tell me the finger, that which finger gives us the direction for the current, which finger gives you the direction for the magnetic field, and which finger
the
gives us the direction of the
second
motion.
finger gives for the current, the index gives for the the magnetic field, and the thumb represents the motion.
Yes, very good, excellent. Now, if you point your thumb, what's the direction for the motion? It's upward. So if we point our thumb upward and we point our index finger into the page, where will our middle finger or the second finger point? All the three fingers, they are always at an angle of 90 degree with each other. They must be perpendicular. So
They must
where
be
will,
perpendicular.
yes, they must be making an
Okay.
angle of 90 degree with each other. So if the motion is upward, if the field is into the page means that your index finger must point away from you towards the screen. Your index finger must point towards the screen. Your thumb must point upwards. Where will your second finger point?
Full point. Yep. So.
Yes.
Where attention the right side is moving. So it's the motion is moving upwards, right? Just moving. Okay.
Yes, yes, the thumb is pointing upwards. Index finger is pointing towards the screen away from you. Where will your second finger point in that case? We are using our right
Towards the
hand.
left.
Yes, very good. So current will
Okay.
move towards the left. So the direction for the current, it would be towards the left. Okay, moving to the next question. Okay, let's take one more example.
Okay.
Okay, if we say, okay, if we are given that the magnetic field into the page, it is decreasing. This is the only information that is given to you. You have to find
Yeah.
the direction of the current.
Okay.
Yes, the magnetic field into the page, it decreases. What would be the direction of the induced current?
Fraction of induced current.
When we only talk about two things.
Okay,
One
so
is
we're
the
using
magnetic
the
field.
right hand grip rule, right?
Yes, very good.
Okay, so into the page
So in the
decreases.
first step,
So
I told you that we have to solve it in three steps. Three steps. In the first step, you have to identify what would be the effect on the flux. Will it increase or decrease? In the second step, using the result that we will get in step one, in the next step, we will identify what would be the direction for the induced magnetic field. And then, using the information in the step two, we will find the direction of the induced current in step three. So we will solve it in three steps. The magnetic field into the page it is decreasing. What would be the effect on the flux?
into the page is decreasing. So the flux is also directly proportional, so it will also decrease.
Very good. The magnetic field it is decreasing, it means that its flux is decreasing. In step
Yeah.
two, we have to identify the direction for the induced magnetic field. If the flux is decreasing, the system will try to oppose this change. To increase the flux, because the flux is decreasing, so the system will try to increase the flux. So to increase the flux, what should be the direction of the induced field? Should it be into the page so that the flux can be increased, or should it be out of the page so the flux can be increased?
The direction of the magnetic
Obviously, it should be
field.
in the
Yeah.
same direction as the original magnetic field so that the total flux can be increased, because we can see right now the flux is decreasing. The system wants to increase it. So to increase it, it will produce the magnetic field which would be in the same direction as the actual magnetic field. So the direction for the induced magnetic field, it would be also into the page. Right? Clear or not?
Yeah.
Okay,
Yeah, it's clear.
induced magnetic field would be into the page. Now in step 3, what would be the direction of the induced current if the induced magnetic field is into the page?
Of the induced current. Okay. It would be, if it's into the page, then it's opposite, right? It would be out because
No,
it
I'm
is.
asking you about the induced current. In step 3, we have to use the right hand grip rule. When we are given the direction for the magnetic field and we want to find the direction of the induced current, we use the right hand grip rule.
Okay. Yeah.
It's right hand grip rule. So you have to simply point your thumb in the direction of the induced magnetic field, and the curl of your fingers will give you the direction for the induced current. So in this case, induced magnetic field it is into the page. You have to simply point your thumb towards the screen, and the curl of your fingers it will give you the direction for the induced current. Are your fingers pointing, curling in the clockwise direction or anti-clockwise?
And so they're curling anti-clockwise.
No,
Wait,
you have to use your right hand. Your thumb
the
will be
flux,
pointed.
I think it's moving downwards, right? So
The flux is not moving downwards. It simply means that the flux is decreasing. You don't have to get confused. What you have to do is you have to simply, in step 1, you have to simply check whether the flux is increasing or decreasing. This is what you need to check. In step 2, If the flux was decreasing in step 1, the induced magnetic field will be in the same direction as the original magnetic field which was given in the question. But if the flux was increasing in step 1, then the induced magnetic field, it will have the opposite direction as the original magnetic field, so that the flux can be decreased. In step 3, you have to simply use the right hand grip rule. Simply. We have no concern with this step 1 now. What we have to do is simply we will use the right hand grip rule. You have to simply point your thumb in the direction of the induced magnetic field, and it is into the page. Into the page means away from you towards the screen. So you simply have to use your right hand. You have to point your thumb away from you towards the screen, and you have to check whether your fingers they are curling in the clockwise direction or anti-clockwise.
Right.
Yes. If you point your
Yeah,
thumb
it's
towards the laptop, what's the direction of the curl of your fingers, of your
towards
right
the.
hand? Towards the
You point the
laptop,
thing.
away from you.
Oh, okay, okay. So the direction of the my fingers is moving clockwise.
Yes, very good. So induced current, it would be clockwise. It would be clockwise. Okay, remember that if you are given the magnetic field which is going into the page, you have to point your thumb. You have to simply point your thumb towards the screen, or away from you. And if we have the magnetic field which is coming out of the page, then we have to point our thumb towards ourselves.
Okay.
Okay, this is how we do this. Let's take another example. Okay, so you're given the magnetic field into the page is increasing around a stationary loop. You have to find the direction of the induced current. What will we do? We are given the information only about the magnetic field, and we have to find the direction for the induced current. You have to
Okay.
again follow the same 3 steps. In the first step, you have to check what will be the effect on the flux. Then in step 2, we will check the direction of the induced magnetic field. And in step 3, we will find the direction of the induced current.
All right.
In step 1, what would be the effect on the flux? The magnetic field into the page, it is increasing around a stationary loop. What would be the effect on the flux? Will it increase or decrease?
It's increasing. So the flux would also increase.
Yes, very good. The flux is increasing. In step 2, we have to check the direction for the magnetic field. Induced magnetic field. What would be the direction of the induced magnetic field? We can see that the flux is increasing. The system will try to decrease the flux because it is currently it is increasing. It will try to oppose it. So how can it oppose the increase? By trying to decrease the flux. So how can it decrease the flux? If the magnetic field is into the page, what should be the direction of the induced magnetic field? Should it be into the page as well? If the current magnetic field is it's into the page and I create another magnetic field, I add another magnetic field which is also pointing into the page. What would be the effect on the flux? Will it increase or decrease?
It will if the flux is increasing, so the magnetic.
No, I'm saying if I have a magnetic field, it is going into the page currently.
Yeah, yeah. Yeah.
Then I add another magnetic field into it, which is the induced magnetic field. I add it into this magnetic field and its direction is the same as the original magnetic field. What would be the effect on the overall flux? Will the overall flux increase or decrease?
It is increasing if they're also increasing the.
Yes, if I create an induced magnetic field which is also pointed into the page, the flux will increase more, right? But our system, it wants to decrease the flux, not increase it because it is already increasing. So what it will do if the magnetic field it is into the page, it will create the induced magnetic field which will be out of the page, so that when they will be in the opposite direction, the overall flux it will decrease. So when the flux will be increasing, the direction for the induced magnetic field it would be the opposite. It would be opposite to the direction of the original magnetic field. Right now it is into the page. That's why the induced magnetic field would be out of the page. If the original magnetic field was out of the page, then what would be the direction of the induced magnetic field? It would be into the page. To
Okay.
oppose the increase, the system tries to decrease the flux. And how it can actually decrease the flux? By simply creating an induced magnetic field which will be in the opposite direction as compared to the original magnetic field. So right now it's increasing, it will decrease it. So it will create an induced magnetic field which will be out of the page.
Okay.
Now we have got the direction for the induced magnetic field. So in step 3, we will simply use the right hand grip rule. Right hand grip rule to find the direction of the induced current. What would be the direction of the induced current?
Right hand grip tool. What is the
Yes,
direction of the thumb? Because I know the magnetic field
it's
are
out of
moving
the
out of the page. Yeah.
yes. So when it is out of the page, where do we point our thumb? When it is into the page, you have to point it towards the screen away from you. And if it is out of the page, you have to point your thumb towards yourself.
Yeah, so it's anti-clockwise.
Yes, very good. So the direction of the induced current, it would be anti-clockwise. Okay, let's take another example.
Which
Hmm. Let's take a numerical problem now.
okay.
Just a minute. Okay, so let's say we are given the numerical that says a rod of length 0.3 meter, it moves towards the right at 6 meters per second on rails in a magnetic field of 0.8 Tesla into the page. The total resistance is 3 ohms. We have to find the induced EMF, the current, the power dissipated, and the direction of the current in rod. Using the information that is given, we have to first find the induced EMF. So which formula of the induced EMF will we use?
Okay. So first the induced EMF, all right.
Yes, we know that we have two rules to find the induced EMF, two formulas. And what are those two formulas? The first one is N times rate of change of flux. And what was the second one?
The second one was to find the induced, yeah. The next one was E is equal to BA sine theta.
No,
BLV
it was
sine
B.
cos sine theta, yeah.
Yes, it was BLV sine theta. So according to the information that is given in the question, which one should we use?
BLV sine theta because we are given the length and
Yes, very good.
the
Whenever
velocity,
I
yeah.
told you, whenever we are not given the theta explicitly, like whenever you are not given the information that it perpendicular or parallel, or you are explicitly mentioned the value for the theta, we consider it as 1. We consider this term as 1. So we have to use the formula E is equals to BLV, but you have to read the statement carefully. Sometimes you may not be given the theta directly as 0 degree or 90 degree, but it may be written in the form of a word. Like maybe you are given that they are perpendicular to each other or they are parallel to each other. So in that case, you have to consider the value for theta, that it's 90 degree or 0 degree accordingly. But in the cases where you are not given anything related to the theta or the orientation, you simply consider this term sine theta as 1 so that we can get the maximum EMF. So the formula, it would become epsilon equals to BLV. Now we will simply substitute the values. So it would become epsilon equals to B is 0.8 times L is 0.3 times V is 6. What would be the answer? We will get 1.44. And what's the unit?
1.44 and the unit is volts.
Okay, very good. It's part A. Now in part B, we have to find the current.
Hmm.
How can we find the current?
To find the current here, we can use the formula E is equal to IR, right? So
Very good. Epsilon is equals to IR. So we will rearrange it. So it would become I is equals to epsilon by R. So it would become epsilon has the value 1.44 and we divide it by the value of the resistance, which is 3. So the value for the current, it would be 0.48. But what's the unit?
it's amperes.
Yes. Now we have to find the power in part C. Which formula will we use to calculate the power? What's
Uh,
the formula that we use to find the power?
Find
It's I.
the formula. Is it only I
Yes,
square R, or could we use the other one also?
yes, you can
VI.
use the other one as well. What's the other one? It's epsilon I.
Okay.
You can use any of these. If we use this one, we have to simply substitute the values. So power would be equals to, it's 0.48 square into R, and R has the value 3. So power would be equals to 0.69. And what about the unit?
The unit is watts.
Yes, it's watts. Very good. Now in the next part, we have to find the direction of the current in rod. So we are given the direction. Moving to the question statement, we are given the direction for the motion. It moves towards the right. We are given the direction for the magnetic field, which is into the page, and we have to find the direction for the current. Which rule will we use?
Okay, to find the direction of the current in the rod. Okay.
We are given two directions. We are given the motion and we are given the direction of motion and the direction of magnetic field as well. So which rule will we use?
The right hand, Fleming's right hand rule.
Yes, very good. We will use the Fleming's right hand rule in this question. Okay, you are given the direction. The direction of motion, it is towards the right. The direction of the magnetic field is into the page. What would be the direction of the current? Motion is towards the right. You have to point your thumb towards the right. You have to point your thumb in the direction of the motion. It's towards the right, so we have to point our thumb towards the right. Then you have to point your index finger into the page. Into the page means towards the screen, right?
Yeah.
Because the field is into the page. So you have to point your index finger into the screen, towards the screen. Where would your second finger point?
The second, okay, we're pointing that towards the screen, and the second finger. The motion is where again? Upwards or down?
It's towards the right. It's given in the
Oh,
question
towards the.
that the rod moves towards the right.
Okay, so in that case, the current is moving upwards.
Yes, very good. The current would be upwards.
Okay.
Okay, let's take today's last question. We are given a coil that has 200 turns and the area is 5 into 10 raised to power minus 3 meters square. It rotates from 0 degree to 90 degree in a 0.05 in a 0.01 seconds of time, and field is of 0.6 Tesla. The resistance is 2 ohms. We have to find the EMF, the current, and the total charge that flows. How will we
All right.
calculate the EMF? Is the flux changing? We know that whenever the area or the magnetic field or the angle changes, the flux changes. When any of these three quantities is it changes, the flux changes, and whenever the flux changes, EMF is produced.
Okay.
So over here we can see that the initial angle it was 0 degree and the final angle it was 90 degree. So using these two values for the angle, because angle is changing over here, we will calculate the two different flux. First flux will be the initial flux, which will be produced when the angle was initially 0 degree. So we know its formula is BA cos theta. B and A, they are constant. So it would be B. B is 0.6 times area is 5.5 into 10 raised to power minus 3 times cos 0. What is cos 0? What's cos 0?
It's I think one, right?
Yes, it's 1. So we have to simply multiply it and we will get 3 into 10 raised to power minus 3. So it would be 3 into 10 raised to power minus 3. Now we have to find the value for the final flux. And over here, the value for theta is 90. So it would be BA cos 90. And we know cos 90 is 0. So final flux would be 0. So to find the change in flux, we have to simply subtract them both. So we will get 3 into 10 raised to power minus 3 because the final flux is already 0. So the answer would be 3 into 10 raised to power minus 3 Webers.
Okay.
Now we have got the value for the change of flux. Now we will calculate the value for the EMF. It's simply N times N is 200s times the change of flux, which is 3 into 10 raised to power minus 3, and we divide it by the time taken to change the flux. It was 0.01. So the EMF produced would be 60 volts.
Okay.
This is part A. In the next part, you have to find the current. Now we have got the value for EMF. We are given the resistance in the question as well. So I would be simply equals to E divided by epsilon
Yeah.
divided by R. Epsilon is 60. Resistance is 2. So current would be 30 amperes. In part C, we have to find the total charge that flows. The total charge that flows. What's the formula to find the charge? If we are given the current, what's the relation between current and the charge? Current is simply the rate of flow
Change of
of charges.
yeah.
Rate of flow of charges, it means that I is equals to Q by T, the number of charges that move per unit time. Rate of flow of charges. Now we have got the current and we know the time as well. So to find the total charges that flowed, we will use the formula Q is equals to IT. We simply rearrange it. Now we will simply substitute the values. It would be 30 times the time was 0.01 and we will get 0.3. What's the unit of charges?
The unit of charge is coulombs.
Yes. So the total charges that flowed would be 0.3 coulombs. Clear?
Yeah, it's clear.
Okay, so we will have the test in our next class. That's all for today. If you have any question, you can ask. Otherwise, let's end the class here.
All right. So yeah, it will be just for numericals, right? Just to
Yes,
get
yes, it will only
get
include the
yeah.
numerical portion. It will
All
include
right.
both the Faraday's law and the Lenz law.
All right. All right. Yeah.
Yes. Okay. Take care. Allah Hafiz.
All right. Allah Hafiz.